Thanks you everyone for joining this, our latest session in our global webinar series. And we have a real special one for you today. Today, I am being joined by our Chief Technology Officer, Phil Lessner, and he'll be covering a look to the future of passive components across the spectrum. So in Phil's presentation, we'll be going through a tour of the electromagnetic spectrum from DC to light, looking at the components and their current and future status across each step of the spectrum. I'll be your host for today. My name is Wilmer Compagnoni, and I lead the technical marketing team at KEMET. And of course, we have Philip Lessner, our Chief Technology Officer. So without further ado, I'm sure we have a lot to get to. I'll hand it off to Phil, and he'll be taking us through this tour of passive components.
All right, well, thank you, Wilmer, for that introduction. So as Wilmer said, my presentation is KEMET covers the spectrum, looking to the future of passive components. And as you said, I'm Phil Lessner, so I'm KEMET's Chief Technology Officer. So just to give you a little bit of background, my background's in chemical engineering. I'm a proud graduate of the University of California at Berkeley. I've spent about 33 years in the electronics industry. 24 of them have been at KEMET in various different research and development roles. I'm now KEMET's Chief Technology Officer, which means I overlook all the product, material, and process development activities across our different product lines. So just a little bit of an overview of today's presentation. So we'll start at looking at the electromagnetic spectrum and where KEMET components fit in the various frequency ranges in that spectrum. And then we'll look at a few different applications and components where we're introducing new products. So first we'll start with low frequency and talk about power holdup and Tantalum polymer capacitors for enterprise SSDs. And then we'll cover sort of a broad range of the spectrum with electromagnetic interference and control products. So we'll talk about XY film safety capacitors for use in harsh environments. And then our flex suppressor material, which is a flexible sheet used for controlling emissions. And then we'll finish out with some really exciting work that we're doing on power conversion at high frequencies oriented toward wide bandgap semiconductor devices, and talk about a relatively new offering that we have in ceramic power capacitors. So let me just give sort of an overview of the electromagnetic spectrum. So that goes from DC at very low frequencies all the way up to visible light and beyond to ultraviolet and X-rays at very high frequencies. The part of the spectrum that KEMET covers in our products are from DC up into the infrared range. So we have some products that are designed for power backup and line frequency applications, like tantalum capacitors and supercapacitors, and then current sensors that go across the mains lines to measure current. And then we have a very wide range of products that really cover the power conversion area. So say frequencies from about a few kilohertz up to a few megahertz. So we have our capacitive portfolio of electrolytic, film, tantalum, and ceramic capacitors. And then we have a wide range of magnetic components, including ferrites, line filters, inductors, tiles, and then composite filters that combine our capacitive and magnetic offerings. So those are used in that frequency range for filtering on the output of power converters, and also for controlling electromagnetic interference from switching power supplies. Then we have our flex suppressor product. So actually that covers we have products that cover a fairly wide range of frequencies from the kilohertz up into the gigahertz now, and I'll focus later sort of on the newer offerings that are focused on 5G and the gigahertz band. And then finally, we also manufacture products that are designed to work with infrared radiation. So those are a series of temperature sensors, and then proximity sensors, which measure human proximity by basically body heat. And those are available both as individual sensors, and what I'm showing here is actually an assembled module with complete electronics to interface it to a circuit. With that introduction, I'd like to move to our first product and first application. So that's power holdup and backup for solid state drives. And that's primarily done with our Tantalum polymer product offering. So first I'll introduce a little bit about the application and market, and then talk specifically about the products we have and our roadmap for improving them. So, really enterprise data storage is driven by the fact that data centers are growing. So servers, have been growing 10 to 20% per year. And that's really because of all the smartphones and tablets and computers that are out there that rely on the back end for things like Facebook and Twitter and other social media and YouTube and all those things. And, that's really mostly what I call unstructured data. So structured data is data that you'd find in a database. And that's certainly, growing, but really the growth is unstructured data like video and images and unstructured text from social media. That's really growing, quite rapidly. And because, that data is growing, that means that there's more data storage needed. And really the trend in the last several years has been the switch from hard disk drives to solid state disk drives. So if you look at the overall growth of solid state and hard disk drives, you can see that they're growing overall, but really the growth is really in the solid state drives. And if you look at just the enterprise segment, which is really where the backup needs are, it's even more dramatic. So the light blue is the solid state drive. You can see for storage in the enterprise, solid state drives are now completely, dominating in the new application, and hard disk drives are shrinking. So solid state drives, I think, is probably most people on the call know, are based on flash memory. One issue is that if there is an interruption in the read or the write process because of a power outage, possibly that memory can become corrupted. Now, in a consumer application, that might not be a tremendous deal, but in an enterprise or data center application, that could be a big problem. For example, if it was a banking application and the transaction was started but not completed, that could really corrupt data and cause a big problem. So for enterprise solid state drives, they require some type of power backup, with the idea that if there is a power outage, this backup capacitor bank will provide the power and energy needed to complete the transaction before the drive shuts down. And then at the bottom here, I'm showing some typical times from these enterprise solid state drive manufacturers that are required typical power and times, range from 8 watts to 30 watts in about 8 milliseconds to about 20 or 30 milliseconds, which gives energy requirements of about 0.15 to about 0.5 joules. So in choosing a power backup solution, there's several considerations. One is getting enough energy so that the board space can be reasonable. Secondly, that these drives are becoming lower and lower profile. So they require, low profile components. And then the third big requirement is long life at 85 degrees C. So typically in an enterprise application, a drive is guaranteed for 5 years at 85 degrees C. So that sort of eliminates batteries, which would be your first thought for backup because they just don't have that sort of lifetime. So if you look at the different capacitor solutions, tantalum polymer, aluminum electrolytic, supercapacitor, and ceramic, actually tantalum polymer fits all the requirements the best in terms of energy density, being able to be made in profiles of 2 millimeters and below, and then having the lifetime for several years at 85 degrees C in terms of capacitance stability and reliability. And what I'm showing here in the top right-hand side of the slide is a typical SSD drive, and you can see the yellow components are the backup tantalum polymer capacitor bank. And there's multiple capacitors used there, and you'll see on the next slide why. So I said that, the energy required are around 140 to 500 millijoules. And if you look at this table, which I know is something of an eye chart, but I'll just, call your attention to the one circled in red, you can see that dense energies per capacitors are on the order of 20 to 40 millijoules. So to make 500 millijoules, then of course you need multiple capacitors, and that's the solution we use today are multiple capacitors, generally in the 6 volt to 35 volt range. So of course the drive manufacturers, they want to save space on the drive and also cost by reducing the number of capacitors. So KEMET's, orientation in this particular area of application is really increasing the energy density of the capacitors. So we want to go from today about half a millijoule per cubic millimeter to almost 0.7 millijoules per cubic millimeter, which is a gain in capacitance or energy of density of about 50%. So how are we going to do that? So we have a multi-pronged effort, but the one I want to talk about that probably has the biggest impact is really packaging. So just to really quickly review, when a tantalum capacitor is packaged, we have the tantalum element, and that's attached to a metallic lead frame, and then overmolded with some type of epoxy resin. So you can see from this diagram that the active element only takes up part of the total package. There's a big part of the package that's either taken up by the lead frame or taken up by the molding epoxy and not available for the active capacitor. And in fact, the efficiency today, so that's the active area or active volume divided by the total volume, is only about 37%. So there's a lot of opportunities for improvement there. So we've already introduced a new product a configuration called face down, where we've improved the efficiency from 37% to 54% by basically putting the lead frame at the bottom of the capacitor. But that still leaves half the package basically as area not available for capacitance. So we have a new packaging development project called KEMET Advanced Packaging, where we're going to take the lead frame out and basically be able to bring the element almost all the way to the ends of the package, and then plate those ends with copper to form the termination for the external circuit. And this also, instead of using molding epoxy, uses an FR4-like circuit board material, so we can make the walls thinner and get even more efficiency. So basically, we'll be able to use about 3/4 of the package at that point in development. So as I said, the face down is available today for order. It's our T523 series, and this KEMET advanced packaging, which will have even better efficiency, will be available for engineering samples now, and then for pre-production samples sometime early in calendar year 2021. So let's continue to move across the spectrum, and now I want to cover some EMI control products. So EMI is or electromagnetic interference is really a issue that affects a large portion of the spectrum, all the way down from power line frequencies up into the microwave region, depending on the application. So I'm going to talk about two products. One is film safety capacitors, also called RFI or suppression capacitors, which are used for conductive emissions at the lower frequencies, and then our flex suppressor product, which is used for radiated emissions at the higher frequencies. So first, let me just briefly give an introduction to EMI, just to calibrate us on some of the terms I'll be using. So EMI is, or electromagnetic interference, is a problem when a source piece of equipment or a source circuit interferes with another circuit, often called the victim circuit or piece of equipment. And this interference can cause the victim circuit to malfunction. And basically, the electromagnetic interference flows basically from the source to the victim by two main paths. One is a conductive path, so that's called conductive EMI, and the other is radiated emissions, which occurs, of course, through the air. So those are emissions that are radiated out of the source and then affect the victim. So there's lots of components that are used in suppressing electromagnetic interference. And I'm happy to report that KEMET makes a large variety of these components. So we're sort of a one-stop shop for a lot of EMI control components. So we manufacture line filters and chokes, both common mode and dual mode products. We manufacture safety capacitors. I'll focus on the film, but we also have a line of leaded and surface mount ceramic safety capacitors, and then we manufacture filters which combine magnetic and capacitive components into one combined device. So these are both catalog products and can also be custom products for a particular application. And then for radiated emissions, we have EMI cores. So these are the type of beads or cores you'll see around power cords to prevent radiation from those power cords. We also make ferrite beads that can suppress radiated emissions on the circuit board. And then, as I said, we have this flex suppressor product, which I'll cover in more detail, which has a wide range of applications for suppressing radiated emissions. So let's start with safety or suppression capacitors, which are mostly film capacitors, but like I said, can also be obtained in ceramic dielectric. So there's two main applications for those. One is the classic sort of EMI suppression application. So they're usually used there in parallel with the mains. So the idea is that the AC line signal comes in, it has noise components associated with it. Those noise components are usually in the kilohertz range, and you want to have a nice clean signal coming out. So you put capacitors in parallel with the mains, and those conduct the high frequency interference either to neutral or to ground. Also, of course, on mains lines, there's sometimes lightning strikes or other high voltage or high frequency transients. So these safety capacitors also need to be able to withstand those events and conduct that radiation to neutral or ground. Because these operate under high stress, these capacitors need excellent safe healing capability. So that's why film capacitors are usually the capacitors of choice. There's two flavors of safety capacitors, X and Y. So X is line to neutral, and Y is the more demanding line to ground. And then there's various subclasses in there, and we won't have time to go into all the details because that's probably a seminar in itself. And in fact, there's been a couple of seminars in that area. And then the other application of safety capacitors is in series with the mains, used for voltage control. So typical applications there are smart meters, control boards, proximity sensors. They are very stable. Capacitance is required, and a tight capacitance tolerance is required over the whole lifetime. Otherwise, the capacitor and therefore the circuit won't function correctly. So just briefly, some standards and tests. Like I said, this is a demanding application, and if the capacitor fails, there could be a shock hazard or even the potential loss of life. So as you might imagine, there's very stringent government standards for certifying these capacitors. So there's standards really across the world, in the US and Canada, in China, and also in the European region. And these capacitors have, after they're certified, they'll have these various markings on them, and then the tests required to meet those standards. So there's usually a test of endurance with rated voltage or above rated voltage. Like I said, these need to withstand usually some type of lightning or other transients. So there's impulse voltage testing. There's, of course, flammability testing, because if there is a failure, the capacitor needs not to catch on fire. And then there's charge and discharge testing that's required. So I want to talk a little bit about environment. So traditionally, a lot of these capacitors, of course, were used in indoor environments for, like your washing machine or refrigerator or some other, type of application like that. That's, generally in a relatively controlled environment, but more and more over the past number of years, there's more demanding environments. So smart meters is one, so they're outdoors. And like I said, they're often, the capacitors there are often used in series with the mains. So they have very tight capacitance and stability requirements. These capacitors are also used for EMI control and green energy type of applications. So that would be solar and wind, again, exposed to the outdoors environment. And then finally, they're used a lot in automotive under the hood applications, which of course is a very tough environment, both from the temperature and the humidity standpoint, because it's outdoors and it needs to work in the winter and cold temperatures, in the summer at high temperatures, and then of course under rainy conditions and humid conditions. So in more recent years, in addition to the tests that I've talked about on the previous slide, there's been a push to qualify these safety suppression capacitors for what's called THB testing. And THB simply stands for temperature humidity bias, and the bias is at rated voltage. And the IEC standard that defines various grades. So there's grades 1, 2, and 3, and then there's test conditions A and B, with with grade 3B, which is 85 degrees C, 85% RH for 1,000 hours, being the most stringent condition to qualify the capacitor to. So of course our long-term goal is to get to as many of our products to grade 3B as possible. And basically, the requirements are around capacitive CF and insulation resistance, but really the most important one that we're testing to is really to ensure that the capacitance after the test is finished remains within 10% of its initial value of capacitance. So this slide shows the KEMET roadmap for film safety capacitors and what we're doing in terms of temperature, rated voltage, and THB grade for the different types of capacitors. So we have X2, X1, and Y2. So I won't go through all the products in the table. Of course, you can download this presentation after the webinar to examine it in detail. But I will note we recently released the R41T series, which is a Y2 capacitor that's qualified to 125 degrees C and the most stringent 3B grade of THB. And then we have a series of capacitors that are under development that are scheduled for release later this year that are going to be qualified to grade 2B or grade 3B. Those are in our X2 series around the 300 and 350 volts. And as a goal, we're trying to also aim to rate these capacitors at 125 degrees C maximum temperature. So you can see we have a very active roadmap in this series, and that's really because you, our customers, have been asking us for these type of capabilities. So I want to go a little bit about the construction of a film capacitor and how we get there. So there's a considerable amount of material science involved. So just to review briefly, a film capacitor is basically a wound element of metallized polymer film. And for safety capacitors, that's almost always polypropylene. We do have some safety capacitors based on paper dielectric that are more specialized, but for almost all our safety capacitors are based on polypropylene, and that's really because it has excellent electrical characteristics and self-healing capability. And then the metallization is usually some type of aluminum zinc metallization, which forms the electrodes of the capacitor. And then the capacitor is put in a plastic box for protection. And then this plastic box is filled with some type of a potting compound to mechanically stabilize the component and also to provide environmental protection for the capacitive element. So the capacitor can degrade several ways in a moist environment. There can be chemical corrosion of the metallization or electrochemical corrosion of the metallization, and also in a humid environment that tends to accelerate the corona effect, which occurs at higher voltages. So that's some type of discharge that will erode the metal electrodes. So from the material science perspective, how do we prevent these degradations? One is by choosing the type of resin for the plastic box. So there's several different types of plastic materials that can be chosen for our most environmentally demanding series. We choose special types of resins that have lower water vapor transmission rates. We can also vary the metallization, so we can control the thickness, and there's a trade-off between self-healing and corrosion resistance. So we do a lot of work to optimize the thickness of the metallization, but we can also vary the composition. So I said we mostly use aluminum zinc metallization, but we've been working in our R&D department on other alloys that have shown some advantages, and we're working on introducing those into some of our products that are on the roadmap. We can also modify the polypropylene film. One important thing is just getting the highest compactness or the highest density and eliminating the air gaps between the layers. And that's really a mechanical thing, but then we can also work on the chemistry by treating the metallization or the film with various surface treatments, which make it more hydrophobic and therefore resistant to moisture. And then finally, the potting compound has a big effect on moisture penetration. So typically in some of our more older and traditional series, that's been polyurethane. In recent years, we've switched more and more to epoxy because that has better environmental resistance and lower water vapor transmission rates. And then more recently, we've introduced more specialized epoxy types that are specifically made for preventing water and moisture penetration in moist environments. So you'll see in our series that we've introduced recently on the roadmap, we'll have a combination of all these material science improvements built in to the component. So I'll finish off here with our life expectancy model. So, we realize that our capacitor may be qualified to 85 for 1,000 hours, but what you, the customer, really want to know is, in my application and at my temperature and my humidity, what is the expected lifetime? So we've developed a tool, which is a collaboration between the film R&D group and Wilmer's group to allow you to predict the life expectancy by inputting the temperature, relative humidity, and voltage of your application. And of course, and you also have to input the product you're interested in because it's product specific. And then the tool will output the lifetime expectancy. And this is a tool that's available on the web. It's part of our KSIM 3.0 suite of tools. So I encourage you, if you have an application for a harsh environment with safety capacitors, to go and to use this tool. We'll also be we're also working on improved humidity resistance for other film series like DC link capacitors. And as we get the data on those other series, that will also be added to this web tool in the future. So now I want to switch and talk about our flex suppressor. So whereas the safety capacitors were more sort of toward the lower frequencies, so line frequencies, and then the harmonics above that at kilohertz sort of frequencies. Flex suppressors are really designed more to operate on radiated emissions and really more in the radio frequencies and cellular frequency bands. So the structure of the flex suppressor, basically it's a flexible sheet of polymer that's blended with micron-sized magnetic powders that are dispersed throughout the material. So basically it's a flexible metal polymer composite sheet. And the way it functions is basically incoming electromagnetic radiation is absorbed by the metal material in the sheet. It's converted, that radiation is converted to heat, and then only a small portion of the incoming radiation is transmitted out. The rest is converted to heat in the flex suppressor sheet. So one of the big advantages of the flex suppressor is that it can be applied to your product in many different ways. So it can be applied to the casing of the product to absorb radiation that's coming from the various electrical circuits in the product to prevent it from escaping from the product. It can also be applied directly on top of components. So these sheets are able to be cut. Since they're soft, they're able to be cut into different shapes, either by you, the customer, or we can, if the application has enough volume, we can actually do custom cutting at our manufacturing facility for you. These sheets do have adhesive backings to be able to be attached to these various either components or the case. Another popular application of the flex suppressor is actually to wrap it around the cable to attenuate radiation from cables. So I had mentioned back in the introduction, we make ferrites that can be go around cables to prevent EMI emissions from cables. So then flex suppressor is an alternative to that. So sometimes it can make a more aesthetically pleasing product than having those big ferrite beads that go around the outside. So that's another popular application. So we have many different flex suppressor products. I won't go through all of them here, but we make ones that have high mu. We also make some more specialized ones that are qualified to AEC Q200 for automotive use. We have products that are able to operate in the gigahertz band and also for near field communications. I've listed here some of our current products, and then we have a roadmap to improve various things like absorbance or frequency response, and some of which I'll touch on. I'll also say the flex suppressor product is available both in roll form and also some products are in sheet form. And then for the products that are designed for wrapping around cables, they're available in thin type of rolls that can be easily wrapped in a cable type of application. So I want to focus on our flex suppressors recently introduced that are designed for gigahertz type of applications and really for 5G millimeter wave type applications. So as you're not familiar with the millimeter wave nomenclature, those are applications in the gigahertz band, so generally around 24 gigahertz or so. So we've released some specific series for attenuation in that range. Our first series released, which was released at the end of last year, is the EFS series, and that's really designed for infrastructure applications like optical transceivers and base station antennas, and that's available in sheet form and thicknesses from about 0.1 to about 1 millimeter. So we've recognized that, in addition to the infrastructure applications, there's a lot of mobile applications, of course, emerging in 5G. So, of course, 5G smartphones are starting to be rolled out, some of which will operate in this gigahertz band. And you can see the projections are over the next 3 or 4 years for 5G smartphone penetration to grow to about 50% of the new phones installed base. The other, mobile application would be in vehicles. So 5G is being implemented in vehicles for advanced driver assist and ultimately autonomous vehicles for vehicle-to-vehicle communication, also for vehicle-to network and vehicle-to-infrastructure communication, and that's mainly because of the very low latency of 5G for these real-time applications. So in recognition that these mobile applications are more space constrained, we were working on the FS series, which is going to be available in a thinner form factor from 25 to 100 microns and in roll form. That product's already passed our internal qualification, and we're expecting the marketing release is going to be coming up pretty soon in mid 2020. So now we have products that will cover both the millimeter wave in infrastructure and mobile applications. So it wouldn't be a R&D presentation without a little bit about the material science behind this. So depending on the frequency that these flex suppressors are designed to absorb at, we need to modify the product morphology and chemistry. So for the lower frequencies, so, in the lower cellular band, we use relatively large magnetic flakes made of iron, silicon, and aluminum in the product. And as we go up into the Wi-Fi bands and then into the gigahertz millimeter wave bands, basically we have to modify the morphology of the product to use smaller flakes, and then ultimately to use micro powders when we get up to the real high frequencies. And we're also changing the composition of the minor elements, silicon, and then going from aluminum to chromium. And you can see in the lower part of the slide here that modifies the frequency range where the device absorbs from low frequencies and then going to higher and higher frequencies. So, I want to leave you with the thought that there's a lot of material science and engineering that goes into tuning these products to work in the right range for your particular application. So then I want to finish off with the last topic, which is high frequency power conversion. So I'm excited to say we've been introducing some ceramic power products that are designed to work in these higher frequency ranges where you need somewhat less capacitance, but you need to have very low losses and often to have a high temperature and capability. So these are being driven by wide bandgap semiconductors. So probably most people have heard that term. And these are basically semiconductors that are based on gallium nitride and silicon carbide instead of the traditional silicon. And the reason they're called wide bandgap is because silicon has a bandgap of 1.1 electron volts, but these other materials have bandgaps about 3.3 or 3.4, so about 3 times the bandgap of silicon. So why use wide bandgap semiconductors? So from the end user standpoint, there's really 2 major drivers here. One is you can get better power conversion efficiency. So this shows some typical power conversion efficiencies for silicon, and then wide bandgap based devices. So you can generally get from 3 to 10% better efficiency by going to a wide bandgap solution. And of course, that's a very big, gain in efficiency, especially when you're talking about high power devices. The other advantage is that you can substantially shrink the footprint of the device. So this figure on the right-hand side of the slide shows a comparison of a system built with a silicon IGBT versus a silicon carbide. And there's a substantial reduction in device size. And we'll explore more on the subsequent slides why. Basically, that's because you can pack things more densely with the wide bandgap semiconductors because of their temperature of operation. And you can also use smaller passive components with those devices. So let's take a look at frequency and other characteristics of wide bandgap semiconductors. So this shows the frequency range of operation of silicon and some of the wide bandgap semiconductor devices, carbide and gallium nitride. So power conversion mainly takes place in the frequency of tens of kilohertz up into the megahertz range. So you can see for the lower frequencies and lower power, silicon is fine, but as you go to higher frequencies and especially higher powers, silicon starts to crap out, and you really need to go to these wide bandgap semiconductors. So high frequency, high power is a big selling point. Also, high voltage is another big selling point because of the higher bandgap, you're able to use higher voltages. So gallium nitride devices will typically operate up to 600 volts, and there are silicon carbide devices already on the market for 1200 volts and moving up to 1700 volts in the near future. And then the third thing is higher temperatures. So silicon devices, as everybody knows, are really limited to operate at 85 or maybe 100 degrees C before a significant deterioration in reliability and lifetime. But wide bandgap devices are able to operate, 150 degrees, and there's even roadmaps to get silicon carbide to 200 degrees. So that's a reason why these components can be packed closer together, because they can withstand the higher temperatures. So if we look at the capacitors and the effective frequency on the capacitive requirement, so I've shown that in the graph here, and what we can see is as we go to higher frequencies, and this is for a DC link capacitor for 10 kilowatt power converter, we need less and less capacitance for the DC link part of the solution. And also as we go to higher voltage, which again I said is another feature of wide bandgap semiconductors, we also need less capacitance. So whereas where we need a lot of capacitance at lower frequencies, that would drive us toward a film or electrolytic solution, which are solutions that provide lots of bulk capacitance. But as we go to the higher frequencies and need less capacitance, then ceramic capacitors become a possibility for the solution. So we've introduced a new type of ceramic capacitor called KC Link. So that's specifically a ceramic capacitor that has capacitances in the range of a few nanofarads up to nearly a microfarad, and rated voltages of 500 volts to 1700 volts, which again covers the frequency range of wide bandgap, and is also rated to 150 degrees C. So again, covering the temperature requirements for wide bandgap semiconductors. So as the name implies, of course, we envision this capacitor be used in DC link applications, but also being used in snubber and resonant capacitor applications. And it really has a very stable capacitance over the entire temperature range because it's based on a class 1 C0G type of ceramic dielectric, as well as a very stable capacitance over the voltage range, and also has a very high ripple current capability, shown here, ripple currents in excess of 15 amps per component for a 3640 size ceramic. But we also recognize that, maybe a microfarad isn't enough capacitance for an application. So we've come up with a packaging solution called KEMET KONNEKT, which is a high density packaging solution, basically based on connecting the components electrically together with a copper tin transient liquid phase sintering technology. Now that's quite a mouthful, but really from a simple standpoint, the copper tin material is applied, and then it's cured at a relatively low temperature, say 250 degrees C, and the copper and tin react and bond the chips electrically together. And once they react, they don't reflow again until you get to very high temperatures, like 400 degrees C. So basically, this composite capacitor made with the KONNEKT technology can then be surface mounted to a board without any danger of the internal connections reflowing. So they're suitable for surface mounting for lead-free reflow conditions. So with the KONNEKT technology, we can make capacitors in 2, 3, and 4 chip stacks of various different capacitance ratings and the voltage ratings that I showed for the KC Link. And this is actually available in 2 different orientations. Standard orientations, which would be a horizontal type of stack, but also an orientation that's rotated 90 degrees, called a low loss orientation. So why would we want to make and offer a low loss orientation? Well, that's because we found that by rotating these capacitors 90 degrees, we can significantly lower the ESR of the capacitor, and therefore lower the heating of the capacitor, and therefore extend the ripple current capability from the 15 or so amps that I showed you on a prior slide all the way up to 30 amps or so at higher frequencies. So that's a big advantage of this low loss orientation for ripple current. The other advantage is we can lower the ESL by about a factor of 4, and especially in high frequency snubber type applications. You know, ringing can be a very important, you know, circuit design issue, and low ESL will help solve that problem. So we're excited to offer, you know, both of these orientations. We also have a very aggressive roadmap for introducing more products based around this KONNEKT packaging technology. So I talked about KC Link, our C0G offering. We also have this available in another class 1 dielectric U2J, which has already found use in power conversion applications. We're intending to introduce X7R, auto grades, specialty grades, extend out the case sizes, the smaller case sizes, which has been a request from some customers. And we've already made in the lab some KONNEKT modules, which combine capacitors and inductors, or capacitors and varistors. So that's a potential future offering, is multi-component KONNEKT product. And then we can also make high capacitance value, high value modules from multiple KONNEKT components packaged as custom modules for custom applications. So that's all on our roadmap for the future. So I want to sort of close by saying, I hope, you know, I've shown you some, you know, of our future products, but I also hope I've shown you that these products are based on material science. So we're an electronic company, but we're driven by material science. And I want to say we use about half the elements in the periodic table in either that go into our components or during the processing of our components. So in addition to the application-oriented engineers that we have in R&D and in the field, we have behind the scenes a large number of material scientists and engineers working on making these components on our roadmap. So if you want to connect with me, I'm on Twitter at P. Lessner, or on LinkedIn. And I've also included my email and mobile phone application, mobile phone number here. So please connect with me, and I'll turn it back to Wilmer to ask any comments or questions that the audience might have.
Yeah, thanks, Phil. And for those of you that may not follow Phil on social media, please do so. He's a good follow, and I promise you, you're not just going to be getting capacitor news. Phil's, I guess, a technologist at heart, and he frequently tweets about things unrelated to passive components. So it's a good technology follow overall. Phil, we got a couple questions here, and thanks for everybody who has sent in some questions. And I'll start it up with an easy one, probably a bit of a softball for you, Phil, is what is the future of aluminum polymer capacitors?
Yeah, that's a great question. So I didn't have time to cover that, but the future of aluminum capacitors is really polymer, and we have some exciting offerings. So in addition to V-chip type aluminum polymer capacitors, we're going to introduce a hybrid version of those, which combine the best of polymer and electrolyte in one product. And we also have, for introduction soon, our axial aluminum capacitors, which are the larger capacitors used in a lot of DC link applications, to be introduced first in a hybrid form and then in a polymer form. So the you know, really the driving thing there is much lower ESR and higher ripple current capability than you can get with the traditional wet electrolyte.
Okay. So next up is the customary 5G question, Phil. So what effects has the now coming up in the advent of 5G and even the trends in automotive, what effect has that had on MLCCs? Is it all about just smaller sizes?
It's not just about smaller sizes, it's also about better response at higher frequencies. The dielectric material that you choose for those higher frequencies is critical. And I didn't actually cover it in this presentation, but I would encourage you to check out our offerings for RF ceramic capacitors. So we have RF ceramic capacitors both available in EIA standard case sizes and also the larger cubic ones designed for higher power applications, and those have specialized dielectrics, and they also have copper electrodes for ultra low ESR, which is another important criteria in the RF range.
Okay. And this is not necessarily a roadmap question, Phil, but is there a way of detecting micro cracks in MLCCs for the purpose of lifetime and reliability?
Yeah, so there is. So we have many ways of doing that. So we can do ultrasonic screening on capacitors to detect voids and cracks during the manufacturing process. So that's typically what we use for in-process. Obviously, we also have extensive microscopy facilities for failure analysis, where we can look at high magnification at those types of defects.
Okay. And because I was privy to this presentation a bit ahead of time, I had some time to formulate a question of my own, Phil. And I was curious, what as you start to develop new capabilities across the spectrum, as you presented here today, what's been the most fun or interesting challenge that you've come across in trying to advance our technologies?
Yeah, so there's a lot of challenges that I think the most fun thing is when we have to invent new compositions to meet a particular component specification. So we do on the tantalum side, I talked about tantalum polymer, and we do a lot of interesting work with the polymer formulations. And then on the ceramic side, there's a lot of interesting work in the dielectric formulation area. So everybody knows that the ceramic class 2 is barium titanate, but there's all sorts of interesting minor elements that you need to add to get the reliability and characteristics that you need, and seeing how that all comes together. Often those projects take a year or two to bring to fruition. Is really satisfying when we bring it all together.
Yeah, it's every time I see that periodic table chart and how many of the elements we use, it's pretty amazing how deep we go into that periodic table. It's cool. It takes a lot of science and work and effort to get these these tiny little components to work as we think they should.
That's right. They're an electronic component, but but behind the scenes, they're powered by material science.
Yeah. So I think that's all the questions we had come in. Before we sign off, I'd like to thank you, Phil. I know, well, actually, we had one last question. Well, we got to wrap it up here. We'll save that for another moment. But I'd like to thank everybody for joining. And thank you, Phil, for taking the time to do this. I know you've got about 10,000 different things to do, and I appreciate the time. And I'm sure our audience also appreciates the time. And I'm sure if they have some questions, they'll connect with you. And thank you, everybody, for joining our webinar. And we'll see you next time. We'll see you on Monday for our next webinar series. So thank you, Phil, and thank you, everybody, for attending.
All right. Thanks, everyone. Thanks, Wilmer.
Bye.